Hey guys, this is our video for 11.7 and it's not out of the book, it's out of class notes. Alright, we're going to start off by talking about the parent function and good grief. Oh no, I didn't want to do that. My pen is just so uncooperative. A parent function is like the simplest version of any kind of function. Like it doesn't have any, like you can see that x squared, it doesn't have a leading, I mean it does have a leading coefficient, it's invisible 1, okay? It doesn't have a plus bx or a plus c, okay? It's still quadratic. If I put the x squared into my y equals, these are the values I get out of my table, and this is the graph of it. So we call that the parent function. And anything we do to it, due to this function, and chiefly we're going to be looking at, I'll leave it to be a surprise. We can add and subtract numbers to the function. We can add or subtract numbers to the x, and that's going to cause translations. And we did translations when we did exponential functions. So let's get into it here, guys. Okay. Let me just cover up and so we only look at one function at a time. Well, that was not effective. Well, we're going to look at f of x equals x squared plus 3. What the plus 3 at the end of the function did, if you notice that the blue function is going to be our parent function, the original x squared, and then the plus 3, you can see this is red. The red function on here, it's the same function, it's just moved up by 3 units. Okay, so adding or subtracting a number to the entire function moves it up or down. And in coordinate notation, the original coordinates, say, at this point here on the blue function would be 0, 0. Let's just look at the vertex, 0, 0. The new vertex is at 0, 3. And again, my pen is not behaving. So the x coordinate did not change, but the y coordinate went up by 3. So that's what coordinate notation means. You're starting off with xy. That every time you do this, you'll start xy, and that represents original function, the arrow, moving to, when I did the translation vertically, the x value stayed the same, but the y value went up by 3. Okay. Let's look at the green one. The green one has a -5 on it. Okay, well what did that do? Well, it moved, you can see the green function is 1, 2, 3, 4, 5 units down from my blue parent function. So as subtracting a number at the end of a function moves it down. And again, my notation, the only thing that changes are y values. X values are staying the same. If this is my blue vertex, my green vertex is the same x value. It's right on the axis, but it's moving down by 5. Okay, and then purple. Although purple was not a color available on the calculator, so I had to go to the closest thing, magenta. And it says +1 at the end, and you can see that the magenta, purple, whatever function moved up 1 from the parent function. So it's y +1 at the end of my coordinate notation. Okay, so what happens if I add or subtract a number just from the x? And I can tell it's only being added or subtracted from the x because it'll be in parentheses with the x. So I have a -3 in this first red function, and draw my black box on here again. I can see that subtracting 3 moved the function 3 to the right. Well, the right usually feels like plus. Well, that's true. It does feel like it would be that. That makes sense. But that's not what happens. Remember, things that in x tend to change signs. Okay? And there's a reason for that, and we'll get more into it in chapter 12. But for right now, you just got to go with me on this. All right? So what do the x coordinates do? How do we do the coordinate notation? Well, let's again look at the vertex. I picked the vertex because it's easy. This is 0, 0. This vertex over here is 3, 0. So what happened? Well, the x coordinate went up by 3, and the y coordinate stayed the same. So the x coordinate went up by 3, the y coordinate stayed the same. And when you're doing coordinate notation, the signs don't do the opposite with the x. They do the same. Whoa, oops. There we go. Let's look at the green function. That says plus 4. So plus 4, as you can see, moved our function to the left. And it moved our vertex to the left. Okay, to minus 4 spaces. So you can see the coordinate notation. Okay. And lastly, our third function, we have a minus 6. And you can see that the minus actually moved our vertex over our whole function, not just the vertex, the whole function to the right 6. And here's our coordinate notation for that. This screen kind of puts both of those things together. I have minus 2 just for the x, so that's telling me right 2, and I have plus 3, which is telling me up 3. So from the blue function to the red function, you can see if I take the vertex, I've moved right 2 and up 3. Right 2 and up 3 with the whole function. Okay? And I just do the coordinate notation as a combo of the last two things. So plus minus 2 would be plus 2, but keep the plus 3. And guys, this should look familiar. X minus 2 squared plus 3. That's because it's vertex form. Alright, and look at here. Negative 2 and plus 3, positive 2, positive 3. That's where our new vertex is. Okay, so a transformation of x squared as the parent function going to vertex form is like doing a transformation. The green one has a plus 4 and a minus 5. And as you can see, that moved it left 4 and down 5. Left 4, down 5. And here's our coordinate notation with minus 4 and minus 5. And a minus 5 moves 5 to the right, and a minus 4 at the end moves 4 down. And here's our coordinate notation, plus 5 and still minus 4. Okay, now for whatever reason this flip chart puts reflecting and dilating in the same thing. Alright, we've kind of talked about reflecting without using that word. Whenever you have a, like if we're going to look at our red, and I think I'm definitely going to want to cover this part up just so we can talk about one function at a time. Alright, so the difference between our parent function of x squared and our new function, the red function, is there's a negative out there, and we all know that that makes the parabola open down. Okay, but it also happens to make it a perfect reflection over the x-axis for the parent function. Okay, so it's not just that it opens down exactly the opposite direction as the parent function. Okay, and this leading coefficient of negative, well, invisible 1 for coordinate form, alright, becomes our coefficient for the y in the second parentheses. And let me just demonstrate why that is. Okay, when we do a reflection, let's say I picked this point right here, that's -2 and 4. And its corresponding point would be -2 and -4. Well, the x value stayed the same, but the y value switched signs. So that's why we went to negative for in front of the y, and the x didn't do anything. If there's no examples on this notes, but there is on the homework, if, and this is not a negative sign, this is shouldn't belong there actually. If the x is negated, okay, we're just putting a negative in front of x, not a negative out in front of the whole function. That would be a reflection over the y-axis, and I'll talk more about that in the homework in a couple minutes. So looking at the green function now, I've got to erase this. Okay. -2. So now not only have we taken look at our function here, this is our original blue x squared. The green one, you're going to notice, not only did it flip over, reflect over the x-axis to open downward, but the 2 made it skinnier. So that's what's the dilation. The dilation is when it's not just, when it's, your coefficient is different than 1, okay? Dilation would mean that it either got skinnier or wider as a parabola, okay? So the 2 makes it skinnier. In fact, as the numbers go higher, and we're talking positive and negative, okay, as your actual number gets higher and higher, your parabola gets skinnier and skinnier. Now, as your parabola gets lower, like starting at 1 and then working back through the fractions, then your parabola widens out. And you cannot have a 0 for a coefficient because that would cancel out the squared term altogether and we wouldn't be quadratic anymore. Okay, so we can see in the next one, what does a half do? Well, if 2 made it skinnier, a half makes it wider. So the negative flipped it over and the half made it wider. Okay? Alright, on to your homework. Now, be careful, because this is not asking you to, what it's asking you to do is compare the first function they give you to the second function that they give you. And for example, if I look down at number 6, which looks like more complex, okay? It's not asking you to talk about the fact that there's a negative sign here and there's a -2 here. The only difference between our original function and our transformed function is the +5. So you're only addressing and talking about what is different from one function to the next. Okay, you're only talking about what's different. Same thing here. You are only talking about what's different. If I look at number 12, the difference between the original function in 12 and the new function is in 12 is there's a -5 in parentheses. And the -5 in parentheses indicates you're going to move your function right 5. We don't have to talk about the -6 because that's in the original function. Here's the reflections, and here's what I'm talking about is if you're negating the x, that reflects over the x-axis. And you can see that it's going to be obvious because the x will suddenly be in parentheses where it was not before. Okay? If you're negating, if you're sticking a negative sign out in front of the whole function, that's going to be a reflection over the x-axis. Okay, so here's a few examples. Actually, that's most of this section done, to be honest. Next is asking you to do coordinate notation. Lots of examples of that from the video. This last section is kind of confusing because they give you a lot of information and then you don't need it. The function is quadratic. Well, I can see that it's quadratic in a later clue because it's got a squared. The function is continuous. Well, it's going to say that every time. The function, I think so. Don't make a liar out of me. Then it tells you that is doing a horizontal reflection of the graph of f of x squared. Okay. And so it tells you horizontal and reflection. And it gives you, the very last clue is really the only one you're going to pay attention to. It says the function is translated 3 units up from f of x equals negative x squared. So they already put the negative sign in for you for the reflection. And all you have to do is put in the 3. Okay? I don't know why they put the 0 there. That was silly. Okay? Number 26. The function is quadratic. Okay, well, that's pretty much what this chapter is about. The function is continuous. They all say that. You can ignore that. The graph g of x is a horizontal reflection of the graph f of x equals x squared. I think they pretty much all say that. So the function g of x is translated 2 units down and 5 units left from negative x squared. So 2 units down would be a minus 2 at the end of the function, plus 5 units to the left would be x plus 5, just adding 5 to the x. And they already told me in this step, I didn't even have to know to put a negative sign in it. They gave that to me in the clue, so I just have to carry that down. So this section's kind of annoying. And then, guys, I am again annoyed, as I have been a few times this year, that in your homework they don't give you a grid. How are you supposed to do a nice accurate graph of your function without the grid? So what you're going to do is you're going to look at it on your screen and just say, okay, so maybe I can see that the vertex is 1, 2, 3, 4, 5, and so negative 5, negative 2, negative 5, negative 2, and something like that. Sketching it in, not exact, okay? I wish it was exact so that we could go to the table and graph it from the table. But they're not doing that. So, whatever. Draw your best picture that you can. Okay? Thanks a lot. See you next time.